the reruns on TV, so
That's right.
that's good as well. Well, good morning. Some of you know me, but I'm Dr. Jonathan Price. I work downstairs. I'm in the geosciences program, and my project this summer is going to focus on looking at the properties of certain minerals in rocks from southern Oklahoma. But instead of getting into the gory details of the project, I sort of wanted to get everybody a flavor of what you can do with looking at rocks and studying them, and some of the equipment that I'm going to use in the process. So kind of a two-part presentation to introduce you to the power of information that's stored in rocks, and then moving on how we can extract that information using the laser ablation system downstairs. So I like showing slides like this. This actually is what I call the money slide in classes like igneous petrology, or in talking to a physical geology class, or even a general class that's dealing with geology, or even going out to grade schools and stuff. Show them an erupting volcano and you've got everybody's attention.
Yeah.
It's 8 in the morning. There we go. Oh my goodness, he's showing exploding mountains. Yeah, no, it's powerful stuff, quite literally. And of course, we're enchanted by, I guess that's a good word for it, by these forces that are greater than us, and certainly volcanoes speak to that. I mean, and in terms of geology, there's a lot going on here in a very short period of time. I think that makes it kind of exciting, because a lot of geology, believe it or not, takes a long time to go to completion. I mean, the Grand Canyon is spectacular, but you know, it's the function of the Colorado River essentially boring its way through those rocks over millions of years. And here we have Mount St. Helens. I mean, this is at 2 in the afternoon. It had been going off since 8:30 in the morning. Still at full throttle here, but pretty much going to die down in the next 12 hours or so. But a lot of energy being released at the surface of the Earth. There's a lot of information that's being preserved for our benefit right here. Well, at least for our edification. We can go in and find out things about the interior of our Earth by what's going on at the surface, and volcanoes are like a fast path to doing that. So even though the activity is very quick, there's a sustained amount of information that's going to live for a long time, actually, and we can go find that. And in fact, a lot of scientists have done this with Mount St. Helens in particular, because it is one of those downstairs. So I like showing slides like this. This actually is what I call the money slide in classes like igneous petrology, or in talking to a physical geology class, or even a general class that's dealing with geology, or even going out to grade schools and stuff. Show them an erupting volcano and you've got everybody's attention.
Yeah.
It's 8 in the morning. There we go. Oh my goodness, he's showing exploding mountains. Yeah, no, it's powerful stuff, quite literally. And of course, we're enchanted by, I guess that's a good word for it, by these forces that are greater than us, and certainly volcanoes speak to that. I mean, and in terms of geology, there's a lot going on here in a very short period of time. I think that makes it kind of exciting, because a lot of geology, believe it or not, takes a long time to go to completion. I mean, the Grand Canyon is spectacular, but you know, it's the function of the Colorado River essentially boring its way through those rocks over millions of years. And here we have Mount St. Helens. I mean, this is at 2 in the afternoon. It had been going off since 8:30 in the morning. Still at full throttle here, but pretty much going to die down in the next 12 hours or so. But a lot of energy being released at the surface of the Earth. There's a lot of information that's being preserved for our benefit right here. Well, at least for our edification. We can go in and find out things about the interior of our Earth by what's going on at the surface, and volcanoes are like a fast path to doing that. So even though the activity is very quick, there's a sustained amount of information that's going to live for a long time, actually, and we can go find that. And in fact, a lot of scientists have done this with Mount St. Helens in particular, because it is one of those rare eruptions to happen in the conterminous U.S. There are Alaskan volcanoes that go off much more frequently, but because it happens in the conterminous U.S., and Hawaii's been going off for quite a while, it more directly impacts us as, you know, a U.S. society in thinking about this, because this, you know, is near a metropolitan center. It's just an hour north of Portland, Oregon, and it's not far from Seattle. So the eruption impacted communities, particularly eastern Washington, and it continues to sort of fuel our interest, because there's a chain of these volcanoes running along the western coast called the Cascades, and all of them are susceptible to these kind of eruptions periodically. Frequencies on, you know, the 100 to 1,000 year scale. So not any imminent threats right now, but nonetheless always thinking towards the future that these are volcanic hazards. I want to speak specifically about how that information is retained over time. I always feel like I need to clarify the nature of igneous materials, because exposure to geology varies from person to person in a lot of different places. People come from different backgrounds. Maybe you had an earth science class, you know, early on in your educational career, or maybe you took a physical geology class. But I'm astounded usually to find that most people are under the impression that there's some great reservoir of melt down there underneath their feet. Depending on who you ask, you know, 10 to 100 kilometers down. And nothing's further from the truth. The Earth is solid all the way down to the outer core. And that's where you encounter appreciable liquids. Except in small locations, the Earth has undergone partial melting. So there's no big reservoir down there of magmas that are just waiting to come up to the surface. I can think of half a dozen sci-fi films that sort of tap into this idea that, oh, we've drilled too far, we've hit the molten part of the Earth. There's no molten part of the Earth to hit. So volcanoes and their counterparts, which I'm going to talk about, magmas intruded into the crust, are localized phenomenon. They only occur where you have partial melting. And partial melting starts with that rock right there. Well, maybe not that rock in particular, although that one came from a volcano. So this particular rock is from Kilburn Hole. It's a small volcano in New Mexico, southeastern New Mexico. What's neat about it is it's coughed up all these pieces of the next layer down in the Earth. So we walk around on the crust, and the layer below it is the mantle. And it's a thick layer. It's almost half the Earth. And it's more diverse than one rock can point to. But this is what it looks like. It's a green rock. It's solid. It's made up of three principal components, and we'll talk more about what minerals are about, but each of those little grain pieces in those are individual crystals, and there's really three types in there. They're iron silicates, so they have iron and silicon and oxygen in abundance, and then magnesium as well, quite a bit of magnesium. This is what you get all volcanic materials from. Mount St. Helens owes its existence to partially melting this stuff. And when you partially melt it, you get a gooey stuff of crystals and liquid rock we call magma. And we keep calling it magma until it reaches the surface, and then we give it different names like lava or tephra, depending on how it comes out. But in the Earth, it's called magma, and magma is just liquidized rock, if you will, partially melted rock. So to be elementary about this, I wanted to talk about, well, how do you get this partial melting in the first place? And you may have experienced this in other classes. So you had Dr. Brink here last week. Did he show you any phase diagrams?
Yes. Mm-hmm.
That surprises me. So Dr. Brink is all about phase diagrams. And it's one of the reasons why we get along. This is what we talk about when we get together at like faculty parties and stuff. Because we tend to see materials. He sees material, stuff you create in a lab. And I see rocks along the same lines. Is that they are responses to physical parameters like temperature and pressure. And in the Earth, those are the two key parameters. Because it gets hotter the further you go down in the Earth. And because you have all this overlying rock on top of you, it gets more highly pressurized as you go down into the Earth. So diagrams like this help me find my way. Now this is a really simplified diagram, but nonetheless it gives us the general point. So again, I'm going to find the laser on this. This was our green rock up here. This is what we're starting with. And for much of the places on the Earth I can point to, it's solid. It's rock. It's not melted at all. So how do we move it from this part of the phase diagram? This boundary in here, this is all solid. So I don't have any scaling on here, but basically we're talking about lower temperatures and higher pressures. You keep all materials as a solid. There are some exceptions to the slope line, but that's basically the general rule for anything. Steels, rocks, it's the same deal. Well, an easier way, and of course the way we fool around with like materials at the surface of the Earth is to melt them by adding heat, right? So we basically are saying, well, let's just go up temperature. I'll keep pressure the same. So in other words, this horizontal line along the pressure space tells us, oh yeah, we're at the same pressure, but what we've done is we've provided enough heat to raise the temperature. And actually I have the arrow going too far, because really all we need to do is get to this point right here. So maybe Dr. Brink talked about this, but these lines are magic. I don't think he said magic.
No.
Dr. Brink saying, this line is magic. This is a magic line where solid and liquid exist simultaneously. And that's a beautiful thing, because that means we've achieved partial melting. That is where things will start to melt. So you'll have some crystals, you'll have some melt coexisting. Well, then we got some magma to work with once you get to that line. So I think that's the most intuitive one. When you're dealing with pressures in the earth, of course, you have variability in pressure that can change depending on, the nature of how thick the overlying rocks are. So if we just change the pressure, we can also achieve the same relationship, right? Where we want to get to this magic line here. Well, if we drop the pressure that's down this way and don't monkey with the temperature, well, we can actually get to that liquid point again. Again, melting. All right, very good. Actually, most systems that we want to talk about are a mixture of the two, so some arrow in between would be an appropriate vector for talking about partial melting. So what I just described are two places where you can expect to get volcanoes, places where you have heating, and the center of our Earth is as hot as the surface of the sun, so heat is being distributed through our mantle, and some places are hotter than others. So we can expect melting there. Hawaii is an excellent example of this. We can also expect melting in places where we've released some of the pressure on top. Decompression, taking the pressure away. So places where the Earth's being stretched, we have a word for these in geology, we call them rifts. These are excellent places where you can expect to have volcanoes and their counterparts, plutons, stuff that crystallizes inside the Earth, because that's where partial melting will ensue. There's a third type. If I wanted to talk about Mount St. Helens, I'd have to mention this third type, because there's another way to get to the liquid part of the phase diagram. I don't know if Dr. Brink talked about this, because they try to avoid this in steel making. But you can add things. Now, if you think about it, there actually is a very good application on some of the stuff Dr. Brink works with. If you've ever done any soldering, you basically want to fuse a metal so that it holds things together and conducts electricity, depending on its application, whether you're soldering pipes or soldering circuit boards. And you do that, you want to find a nice metal that does that, but you don't want to apply a whole lot of heat because you don't want to melt the circuit board or mess up your pipes. So you add a flux to it, right? You might have seen this if you played with solder. Some of them come with flux, some of them you add flux to them. Flux is just a Greek word for flow, and it's a cheating trick. It's adding another component in to lower the melting point is one way to think of it. But it's really lowering the melting curve in pressure temperature space. In other words, it takes this straight line, if we look at this subset right here, it takes this straight line and moves it over. And usually they don't have nice straight line configurations anymore. And it's dependent on how much flux you put in. So you put in a little bit of mixture, you get a little bit of movement of the line. You put in a lot of mixture, you get a lot more. The flux of choice in the Earth is water, although we can also talk about CO2 as well, because these are abundant components in the Earth. Not a flux you'd want to use for soldering, because the water would just evaporate. But under pressure, the water will stay there. If we wanted to talk about the kind of magmatism we see in the Cascades, we need to discuss this because basically they're a product of water being introduced to our mantle on the offshore subduction zone. So 3 ways to get partial melts. That's one of the take-home messages for today. You get it by either raising the temperature, dropping the pressure, or adding another component, think water, when you're thinking about the Earth. And again, these apply to all materials, so if you're not all that interested in rocks, well, you can apply this to steels and ceramics and whatnot. It all works the same. Alright, so we know we can get partial melts, and we know we can only get them where these things are happening, and that turns out to be highly localized places in the Earth. And the Earth is old, 4.5 billion years, so these places have moved around from time to time. And sometimes we sort of create these magnetic products and lock them in, and they're just stuck there and nothing else happens to them. Well, we can go and look, even though they're very, very old, and say, this is what the Earth was about many, many years ago. So if we got partial melts, the next question is, well, how did they get to the surface? You said you're melting green rocks in the mantle. Well, when you melt these things, they have a lower density than the surrounding rocks around them. And that means they'll try to move upwards. We're in a gravitational field driven by the Earth, so buoyancy forces dictate they'll move upwards. Now, we're moving through rocks, so you have to either flow the rocks around, which is possible deep in the Earth, or you have to break the rocks, which is more what I want to talk about because it's a little more understandable. You have to break the rocks through fractures and fissures, and that allows the rocks to move up and down well to each other. The solid rocks to move down and the liquid rocks to move up. So either they make it all the way to the surface, which was the point of the Mount St. Helens slide, either they form these nice powerful volcanoes, or they don't make it all the way. And actually, the fate of most magmas is probably this: they don't make it all the way. A small percentage have the, what we call, driving pressure to make it to the surface. It's really a function of buoyancy forces. And again, if you're using water to create these things, and in all cases we're using a little bit of water, that's adding to your buoyancy force as well. That's making things a lot lighter in the magma than it is for the surrounding rocks. This is a highly simplified picture, but this is not unreasonable for some settings, where you can expect volcanoes to occur where you have breaks going all the way to the surface, but plutons, or what we call plutonic rocks, rocks that are crystallizing at depth, at some